I would like to start a bit more theoretically about designing electronic music instruments. How you do that? How do you design electronic music instruments? Because it's not something that you just sit and do. There is actually quite a lot of things that are involved and a lot of theory and stuff. As far as I know, there is no school in the world where you can go to and do a course in designing electronic music instruments in a proper way. So it is something that is mostly done by larger companies, and they over time develop a certain method on how to do that. I also had to basically design a method to do it. And the advantage of using a method is that if you have a good method, it allows you to actually do anything that you want. And that is a very interesting thing. And I would like to share that with you today and tomorrow and with the people on the internet. So if you have an electronic music instrument, it means that it is an instrument meant to make electronic music. And there is a difference, in my opinion, between electronic music instruments and electronic musical instruments, because electronic musical instruments are musical instruments that just happen to use electronics in their technique, so that are also electric pianos and organs and stuff like that. But I think that if you say electronic music instrument, it is an instrument that's specifically meant for electronic music. Now, if you want to make such a thing, you first have to come up with a concept. That is always where it starts. So, and because you are designing something, you start with the conceptual design of the instrument. So, I'm not want to go really deep in the conceptual design, because actually it is a very broad subject. I could speak about that for maybe weeks. It involves all sorts of things like philosophy, etc., etc., etc. But what is defined in the conceptual design, for instance, is first of all, the most important thing is the purpose of the instrument. What is it going to be used for? But there are all sorts of ergonomical things, how it's going to be played, the size, but you're also talking about materials and looks and portability and many, many, many kind of things. But the most important thing, of course, is the purpose. And for us, the purpose is very simple. We're going to make electronic music with the thing. So if you have an idea of the concept of some, let's say, some new instrument, then the second level is basically the functional design. And in the functional design, you basically just make a list of all the functions that you want in that specific instrument. Design. I'm talking Dunglish, not English. And that was some Dutch thing. So basically, if you create an instrument for electronic music, you want to have functions. But of course, you have to also know what you're working with. And what you're working with is sound. Everything that you do has to do with sound. And some people may think that if you make an electronic instrument, that it's about electricity and voltages, and maybe it's even a digital instrument, so it's about bits and bytes and samples and stuff like that. Well, it is, but that's actually on a lower level. On the main level, you're working with sound. You're always working with sound. You're producing sound and you are processing sound. So you have to ask yourself the question, what is sound? And it's very important to give that a really deep thought. What is sound actually? Because we sort of take it for granted. But if you really want to have control over what you're doing, you have to know what sound actually is. So basically sound is a physical phenomena that takes place in a space. So that means that sound by default is a three-dimensional phenomenon and not a two-dimensional phenomenon. But you can be easily put on the wrong foot, because if you make a recording of sound on a computer, you can actually see the sound recording on a two-dimensional screen. So you might actually have the conception that, well, sound is a two-dimensional thing. No, sound is only sound when it's actually in the space. And that is a three-dimensional situation. So the moment when you make a recording of the sound, you know, the recording may be a two-dimensional thing, but that is only the representation of the sound. It's not the sound itself. And that brings us back to some nice old Chinese philosophy, because I remember I once read a book called the Tao Te Ching, and that starts with the phrase, the Tao is not the Te, the name is not the thing named. And I think that Shakespeare also said something about a rose is a rose by any other name. Isn't that Shakespeare? Mm. And this basically also applies here. You know, you have to sort of always realize that what you're working with is something that is in the space where you're in and that you're hearing in that space. So all these functions that you want in your instrument will operate on sound. And sound basically is a vibration of the air, it's waves. So you're always working with waves. And you can apply all sorts of computational processing on wave phenomena. And luckily it's not very complex. Basically it all starts, the mathematics that describe what you can do with waves were already sort of figured out by people like Isaac Newton, because waves are produced by some movement, and the most simple movement that you have is a rotational movement. And when Isaac Newton sort of figured out all this mathematics that have to do with how planets rotate around suns, etc., that describes basically rotational movements. So if you would sort of transform a very simple rotational movement to a sound, then actually what you would hear would be this. Maybe a bit louder. And you would hear a sine wave, because a sine waveform is basically produced by a rotation. And the sine wave also lasts in time. So the way how you can sort of transform a rotational movement into a sine wave is like, for instance, if you have a bicycle wheel, just imagine that this bicycle wheel is here, and we put a little lamp on the side of the bicycle wheel, and we turn it. Then this little lamp will make a vertical movement and a horizontal movement, and if you would plot that on a paper, you would actually produce a sine wave for the horizontal movement and a cosine wave for the vertical movement, vice versa. Then it becomes interesting, because let's say if that wheel that is turning like this is also moving towards you while you turn it. then you would actually produce a spiral. And basically, you can sort of express sound in 3 dimensions by having a horizontal and a vertical movement, which is basically a sine and a cosine wave, and then how it sort of moves towards you or away from you would be the time that elapses. And this principle is used a lot in the synthesis of sounds, and it's also used in radio technology, where you also have to generate sine waves. And most of the mathematics and techniques that have to do with this were already developed almost 100 years ago.